heat released.
Yeah, but that's what I guess what I'm saying is most of the time you would be doing it at a set pressure.
Yeah.
So in that case, the pressure change term is not going to be it's not going to account for much over the course of your simple reaction. That's the same reason you do it at like
No, but the
pressure.
differences between the entropy and the heat of adsorption has to do with the free energy and the heat of adsorption has to do with how much entropy is lost upon adsorption. And it's not a negligible amount, because I'm going from a gas phase molecule that can zip around in all 3 dimensions to something stuck to a surface. Yeah.
One of the things you could do to prove why delta H would dominate is if you calculated delta H and delta S. Delta H would depend upon Cp times T2 minus T1. S would depend upon the natural log of T2 over T1.
There are a lot of adsorptions where if you leave this out, you're going to come to the exact wrong conclusions.
Right.
So this is not a negligible thing for adsorption processes. It is somewhat negligible for surface reactions. But you have to understand that you lose a ton of entropy in going from a gas phase molecule to going to something stuck to a surface.
That's the difference that I wasn't accounting for with calorimetry. Is you're right, there's a phase change, but if that's the case, how on earth does the free energy equal to the enthalpy?
Oh, I didn't say that they were equal. I just said that depending on what you're looking at, you can see that all 3 of these can be reported.
Oh, okay.
Yeah, but they're not equal to one
Because I
another.
was
Sorry.
reading those being
No.
equal, so-
What is that? Is that like the backward, what is that? The sigma or what is that? No, it's in front of the CO. Like the CO plus an 0. Is that 0? Oh, 0 energy. Okay.
This. Yeah, I was just putting a scale on the reaction coordinate diagram. That's 0. All right, so let's talk about adsorption kinetics. So here's my reaction, is A plus star goes to A star. Is this reversible? Yeah, adsorption and desorption can both occur. The other way that this is written in the book is A plus S goes to A S. So the Fogler uses S for star or site. Most people in catalysis literature use an asterisk to represent a catalytically active site. So let's imagine, because this is an approximation that simply works well. So we have some grid of sites. And we can adsorb to any of these sites. And so we have a site balance, total sites. One is constant, right? I'm not changing the number of sites as I adsorb, not the total number of sites. And it's equal to the number of vacant sites plus the number of adsorbed species. And so I can write this in terms of concentrations as we've done other things. So the total concentration of sites is a constant value. It's equal to the number of empty sites on our grid plus the number of A star species. Now, of course, if I have more than one species present, I would have to add in terms for those as well, right? B adsorbed to the surface in this example. That's all we had was A and B, but in real examples, you might have 20 different species which can all bind to the surface. So the number of sites, just to put a number on some of these things, for a close packed surface, to give you an idea, 10 to the 15 sites per centimeter squared. And this is for a closed packed metal surface. For example, platinum 111. I don't know if you guys have had any crystallography yet or anything like that, but if I take the 111 Miller index of a bulk FCC metal, which is platinum, you get a close packed surface, and I'll send out a picture of what that looks like. Another unit that's common here is instead of sites per centimeter squared, is you can do moles, and you can have a mole of a site just like you can have a mole of A per gram of catalyst. So this is something more common, and the way that you deal with grams of catalyst is you have to relate to, all right, if I have X grams of catalyst, how much surface area do I have? Right? And if I know the surface area per gram, then I can relate between those two species, the sites per centimeter squared and grams per, or moles per gram catalyst. Yeah?
This is just the sites where things can absorb, but not necessarily the reactive sites for the reaction.
In the case of adsorption, let's say in this class, we're going to ignore the difference between an unreactive adsorption site and a reactive adsorption site. But right now what we're talking about is specifically chemisorption on something like a metal surface where all the sites are active. Obviously things get more complicated if you have inert sections within that cycle. Okay, what else? Yeah, so again, like we mentioned, this is a gram, this is an area. So there must be something to relate the two. A typical surface area for a catalyst . 50 to 300 meters squared per gram of catalyst. So just think about that for a second. If I have a square meter, that's a big area, right? I mean, you guys can, that's not like square, that's not square nanometers. We could draw that down on the board. I can get 50 to 300 of those in a gram of catalyst, which looks like to you a tiny amount of sand in a bottle. So the reason why they have high surface areas is because of all these tiny, tiny, tiny pores. Well, all that internal area is actually what we're counting. So the surface area for a catalyst is very, very high on a per gram basis. All right, another definition. Let's define coverage. So the coverage of species A is equal to the concentration of A on the surface, right? And again, you might see me sometimes put A star there, divided by what? Yeah, the total concentration of sites. So if I fill up my checkerboard, what coverage am I at? One monolayer is what we call that. And so again, you can also write this as the concentration A star over, I haven't defined that one yet, but usually L in catalysis means total concentration of sites. That's another way to account for the total concentration. So these are the same. Don't let it fool you that, but this is what Fogler shows you. This is what everything after Fogler that you might do, that's what you'll see. Yeah?
If you had a bilayer, wouldn't your theta still always equal 1? Because you still have
Yeah, this is just for chemisorption. So yeah, this is chemisorption, right? I'm making so I can't make bilayers. I mean, technically in a research sense, you can go over 1, but we're not going to talk about things like that. All right, so the concentration of vacancies is equal to, or excuse me, the coverage of vacancies is equal to that, right? It's also equal to 1 minus the coverage of my bound species, right? So if I'm at 1 monolayer, that means I have no vacancies left. I'm at a coverage of 0. Yeah?
No, this is just because you have one species and all
Yes.
that be summed over all species? Right?
Yes. Yes. In a real system, that would continue out for however many species you have. Now, in reality, when you have a system, it might have 200 species, but the vast majority of them are present at concentrations which are negligible. And so you approximate it by saying, I'm going to have CO, I'm going to have vacancies, everything else is there but not really. All right, so how can we model this adsorption process? You have the rate of adsorption and we'll explain what some of these are. So why does he have sticking on here? All right, we'll come back to that. All right, so I can write a rate based on a sticking probability and a flux times the coverage, because I can only absorb, or times 1 minus theta A. So what is 1 minus theta A? The coverage of vacancies. Well, I can only absorb the vacancies, right? So the rate of adsorption goes to 0 as the coverage goes to 1. And that makes sense. I can't adsorb if I'm fully covered. So again, this is a sticking probability. It shows up later in the notes. Here's a flux, which is equal to the concentration times the molar velocity, or the average gas velocity. And I can rewrite the concentration. This is in the gas phase, by the way. This is not the concentration on the surface. Everybody see that? This is Ca. Back here we have Ca